Let's start with a few reminders from last time. So what did we talk about last time? Multiple extension, right? And we talked about the general case, okay? The multiple expansion that we can write for anything, for any charge distribution, whether it is a dipole or a quadrupole or a monopole, okay? And we also talked about the specific cases of physical objects that just happen to be monopoles or dipoles or quadrupoles, okay? We separated both of the things. And I told you that in the case of these specific objects, what is the potential? Okay, so you remember? So we had these are the reminders. Okay, we saw that in any situation we can write the potential in the following form: 1/4 pi epsilon 0 q over r plus p er over r square plus half of er q er over r3, etc., etc. Okay, so this is in the general case. Okay, and then we said, okay, we gave names to each of these terms. We said this is the monopole, this is the dipole term, this is the quadrupole term. Then we asked, okay, why do we call them this way? Because in the specific case of a physical monopole, okay, which is the case where we have one charged particle, the non-zero term, the only non-zero term is this one, okay? And in the case of a dipole, the first non-zero term is what? This, okay, and it's also the dominant. And then we said in the case of a physical quadrupole, the first and dominant non-zero term is this term, and this is why we call them this way. Okay? Rings the bell from last time? Okay. And we also did this small table, right, where we had the general case, physical monopole, physical dipole, and physical quadrupole. Right, so okay, and we had, so we call these terms A, B, C, B, C, okay, and we saw that in the case of a physical monopole, this is 0, this is 0, then this is 0 and 0, 0. Okay, here we defined I remind you what the dipole moment is. I'm taking a few minutes to remind all of this because we're going to use it a lot today. Okay, today we're going to talk about electric fields in matter, and the way we model matter is with many small dipoles. So we will need all these things today. Okay, so I have this P er 4 pi epsilon 0 r square, okay? And is this 0 in the case of a physical dipole? Is C 0?
Yes.
No, it's not. It's not 0, but this term is the dominant one, right? And okay, and this we didn't calculate. So what I will do now is to calculate the is to calculate, to give an example and to calculate this term in the case of a physical quadrupole.
Didn't you say that for monopoles, the dipole can also be not zero?
Yes.
Obviously, it's not in the origin.
Right. We said that if we're not in the origin, that the only case where it will be exactly the monopole term is if we have a charge in the origin. Right.
But it's
Okay, so what I will do now is to give you an example of the of a calculation of C, because you might need it in the exercise. Okay, so let's start with the physical quadrupole. I remind you that a physical quadrupole is just two dipoles alternating dipoles. Okay, so plus Q minus Q. Plus Q minus Q, okay? And I have here a system of coordinates. Oh, here I have a point M, okay? And this I will call D. This I will call D star, okay? And this distance here is A. Okay, so if I write the coordinate of D, it's, you tell me what are the coordinates of D? It's a square. Okay. What are the coordinates of D?
A over half x.
Half of A, right? And
X,
0 and A over 2. Okay. And this star is minus A over 2, 0, A over 2. Okay, so this is X and Z. Okay, Y is perpendicular to the board. Okay. And okay, so let's write the dipole moment in this case. So by definition, when I have a discrete distribution of charges, the dipole moment is the sum of Qi O Mi. Okay, so in this case it will be what? What is going to be the sum of these?
0.
0, right? Okay, and it matches what we said, that in the case of the quadrupole, the first non-zero and dominant term is the quadrupole term. Okay, and Qij, I gave you the expression for it at the end of last time. So we said that Q is a tensor, it's a matrix. So we will talk a bit about tensor again today. And it's a matrix, and I gave you the formula to calculate the various terms of the matrix. So it was the following. I simply want to give you an example of applying this formula. Okay? Square 2 rho. Okay? So this was the formula I gave you. Okay? And so we will not calculate all the 9 cases, but I will give you a few examples, okay? And I will also give you the final result so that you can check at home that you agree, okay? So Q1, okay, so in the case of Q1, R prime is D. Okay, so it's this. Okay. Okay, so eventually Q is going to be equal, the total Q is going to be equal to Q1 plus Q2 minus Q3 minus Q4. Okay, so this Q1, this is for R prime is equal to D. Okay, this is for R prime equal to minus D. This is for R prime equal to D star. And this is for minus D star, okay? But I don't want to waste too much time and calculate each of these terms, so I will calculate two of them, and you'll see how we do the calculation, and you can check at home that you're recovering what is needed. Okay, so let's start with Q1. Okay, so I want to apply this formula where R prime is D. Okay, so this is a 3x3 matrix. Okay, do you understand what I'm doing here? So, okay, so here, this is a matrix, okay, and last time I gave you the terms of each of these, the way to calculate the terms of each of these matrices. Okay, now, so each of the charges will correspond to a situation of one of the deltas being 1, okay? Right? This is an integral way of writing it, but because we have discrete charges here, okay, so when R prime is equal to D, this delta here is going to be equal to 1, okay, and then you need to replace the relevant R's in the integral, and it gives you each of the terms of the tensor, okay? Makes sense? Okay, so let's start with the Q1. Okay, so in the case of Q1, okay, this R prime here is equal to D. Okay, and I have Ri and Rj. Okay, the R's are the ONs. Okay, and the R primes are these. Okay. So I'm getting here a squared over 4, 0, 3a squared over 4, okay, and here, so Q22 is going to be 0, 3a squared over 4, okay, I'm just replacing 0, a squared over 4, 0 and minus a squared over 2. Okay? So you simply need to replace in this equation R prime with D, okay? And do the sum. Okay, and I will let you check at home that if you do this for each of the terms, you will get that the total Q, which is this sum, okay, is equal to Q 0, 0, 3a squared, 0, 0, 0, 3a squared, 0, 0. Okay, this is this sum. Okay, but now we want to use it in this integral, right? It's not enough. Okay, I feel like I've lost you. So what shall I do? So the total Q, the Q here, this is a matrix, okay? And this matrix is obtained by summing the contributions from all the charges. Okay, if I had a continuous distribution of charges, it would be an integral. If I have something discrete, it becomes a discrete sum of several matrices, okay, which are non-zero where delta ij is 1, okay? And if you replace Ri, Rj, and I prime for each of these charges, okay, I remind you that R prime is the way I point to charges. R is the way I point from OM, okay? So R prime is what tells me where the charge is. And if you replace, check at home, okay, that this is what you're obtaining if you're replacing R prime here by D. Okay? So if you do this for each of the charges, okay, you will obtain 4 terms for Q. And when you sum them, you will obtain this. Now this is not enough. What we want eventually is to calculate the potential. Okay, so we need to do the following. We need to calculate half of, okay, so half of Q, if you remember from last time, I also wrote it with I wrote it in 2 different ways. In one of the ways I had here R3, okay, and the other ways to write it, I had here a factor of 5, but here I had the actual R here, which cancels, remember? Okay, so I'm just replacing 0, 0, x, oops, past the line. Okay, so VR is equal to half of QR over 5, x, y, z, 0, 0, 3a squared, 0, 0, 0, 3a squared, 0, 0, x, y, z, okay? And this, if you do the matrix sum, this gives you q over 4 pi epsilon 0 r5, 3a squared, xz. Okay, so this, just check that if you do the matrix calculation, you will get to this. And by the way, for those of you who work with Nadav Schneer's book, which I really recommend, it's a really good one, there is a mistake in the book in this calculation, and so that's okay. It's in the list of mistakes published for this book. Okay, so it's just an example. What did we do? We calculated the term C for a physical quadrupole. We got its value, and we also showed that it's non-zero. Okay?
Can you explain what Ri and Rj in the formula are?
Yes. So I'm trying to see if I wrote it last year in a more okay, so first it's good that you ask this because here there is a prime, okay? There are 2 primes. Okay, so the r's in this integral are pointing at the charges. Makes more sense now? So Ri, Rj, if we're sitting here on here, we're summing 3 times, so Ri, you need to do it for all the terms, okay? But if you're sitting here, it will be A over 2, it's written here, okay? So, you understand? It makes more sense now? Ri and Rj, as well as R prime, are always pointing me to one of the charges. It's a sum over, it's like the superposition principle. It's a sum over all the contributions from all the charges. Okay, so you just need to write the Ri's, Rj's with this, okay? And then wherever you sit, you will get one of the deltas to be non-zero. Okay? Makes more sense? I just forgot the points here, okay? Okay, so this brings us to our next chapter, which is, today we will talk about electric fields and matter. And the reason I spent time reminding things is again because we're going to use a lot of dipoles in the following chapters. So can I remove this?
Question?
Trying to see if I can add one line that will help you. Okay, I'm going to add one thing. So this, I want to help you for this calculation. So 1 second. Okay, so this row R1 is equal to Q delta 3 of R prime minus D. Okay. You agree? Plus minus Q over delta R prime minus D star. Plus Q of, it's a delta cube, right? A delta function of R prime plus D minus Q of a delta function of R prime plus D star. Okay, so these terms will cancel whenever you are not on one of these charges. Okay, so this should help you. Okay, so third chapter is the following: electric fields in matter. Okay, so we're still, yes. What's תזכיר לי את השם? ינון.
How do we calculate Q in the general case when it's not a physical quadrupole?
So this is the integral in the general case.
But the index I and j is going to be infinitely many charges to some, no?
So the integral is on R prime, and you will get, so the tensor will be 3 by 3, but each terms in the tensor will be the result of an infinitesimal sum of these things where R prime and Rj are all over your distribution.
Yes, R prime is summing over the whole shape.
Yes, but R prime I and R prime J too.
Okay, is it how do you
RJ and R prime aren't the X, Y, and Z of R?
אפשר להראות דוגמה של ממש חישוב של הדבר הזה?
זה הוקטורים שהולכים לכל הארבע מטענים. זה המקרים של כל...
אבל ה-IJ פה זה it's the coordinates. R prime I and R prime J are coordinates. X and Y, I and J. So I and J are the coordinates. Okay? And
so it's not a vector? It's not a vector then?
no, it's a tensor. It's a 3 by 3. So if you have X, Y, Z, so this will be X and Z for the coordinate.
But that's not
0,
what we did
3,
here.
2. What?
That's not what we did here.
It is what we did because
But
in this case it's two-dimensional.
So how it became 0, for example, במקום 1, 1, איך קיבלנו מינוס A בריבוע חלקי 2?
כי ב-Z אין לי... כי שמתי את הקוואדרופול שלי ב-XZ. XZ. XZ.
יש נגיד עבור X.
אוקיי.
זה בסדר? זה מובן? אני מציעה, אוקיי, I suggest that I will put on the Moodle the detail. There is a value in you doing it. It's pretty simple matrix calculation, but I see that I'm a bit losing here. Okay, so I suggest that in a week, try to do it. Okay, try to recover it. And in a week, I will put a detailed calculation, not of all the Qs, okay, but let's say Q1 on the Moodle, if it's still not clear, okay? Okay, so let's move on to electric field in matter. So we're still in the context of electrostatics. ינון, זה בסדר? זה בסדר לך? Okay. IJ coordinates.
Yes.
The R primes are pointing to the value, to the charges. If it's continuous distributions, you're integrating. If it's discrete, you've got deltas and you're in a good shape. Okay? So, okay. So, and I think there is also an exercise in the tutorial about this. So, you wanted to ask a question? Okay. Okay, so we're still in the context of electrostatics. Okay, so no movement, no waves for the moment. But now we're moving into matter, and at some point we will generalize whatever we're doing for electrostatic in matter to non-static situations. But we're starting with static situations still. Okay, and I will start, so part of today will be me telling you stories, okay? There are several types of materials, some are called like this, some are called like this. I'll give you all kinds of definitions, okay? And then we will go into more formalism, but part of today is defining different types of materials, for example. So until now, we had two situations. We had, in terms of charge distribution, we had one situation where we were in vacuum, right? We were sitting in vacuum and asking, okay, what? I have a charge here, I'm here, and Maxwell's equations are local, so I can use it locally in vacuum, and I'm asking what is the field created by a given charge at the point M in vacuum, okay? And we had another situations in exercises where things were in contact with a conductor, okay? So we had a way to impose the potential, okay? So we were either sitting in vacuum or in contact with a conductor that was either grounded or not. Okay, these were the two situations that we encountered in exercise. Now we are in the third situation where we are sitting in matter. Okay, this is the situation that we will explore today. And we will be asking, okay, I'm sitting inside matter. What is the field E that is generated inside the matter? How will this matter react to a field E, etc. Okay, so it's a third configuration. And in this context, we have different types of materials that we will talk about. Okay, so different types of materials. Okay, so there are basically two categories, type, and in each of these categories the charges will be different. Okay, so the first category, which we already mentioned, is conductors. And the second category is insulators. And we will call them dielectric materials. Dielectric materials. Okay, so let's think about an example of a conductor. Metal, okay, any metal, and of an insulator. wood, but also water. Okay, we will use. It doesn't match the way we imagine someone getting electrified in his bathtub, but water is also dielectric for our purpose. Okay, so water, wood, etc. And what are the charges? So in the case of a conductor, what are the charges that we're talking about? They are called free charges. Okay, they are charges which are free to move inside the material. So for example, in a metal, what are the free charges? Electrons, okay, so each atom will have 1 or 2 or several free electrons that will be free to travel in the material. Okay, and here, in the case of insulator, we have charges which are called bound charges. Okay, and what is why do we call them bound charges? Because they are bound to the nuclei of the atoms. Okay, and they can move, but they are limited within a certain limit. Okay, so what happens if I put a conductor in the field E? Okay, I remind you that this is always the question. I'm imposing E. What happens if I have a conductor? I'm putting a conductor in a field, in an electric field E. What happens?
The charges move.
What?
The electrons move, canceling out the field.
The electrons move. Okay, we talk about the new field which is induced by this, but the electron moves. There is a current. Okay, electric current. So if I put a conductor in a, effect of E. Okay, so current, the electrons start moving, and have a current. What happens if I'm putting an insulator in a field E? What is so the naivest answer is what?
Nothing.
Nothing, right? This is the naive answer. It's an insulator, nothing happens. But why isn't it exact? Because at the scale of the atoms, there is no such thing as neutrality, right? I have areas with negative charges and area with positive charges, and there is, apart from neutrons, there is no such thing as a neutral area, and so locally, the field E will act differently on the positive area and the negative area, okay? But this is exactly what we will ask today, okay? Today we will ask, I'm putting this material in the field E, what happens? Okay, and we will also ask something else, because as, is it Ariel? No, behind you? Itai, sorry. What Itai said is that there will be a field that will cancel the original field, etc. So we'll see later that insulators themselves will generate a field. Okay, so today we will ask two questions. We will ask what happens to the insulator when I put it in the field, and the second question we will ask is what is the new field, the second field that is created by the presence of an insulator over the electric. Okay? Okay, and from now on, I will focus on this. Okay? Everything I will say now, all the stories I will tell you about different types of subtypes of materials is zooming on the electrics. Okay, I'm putting conductors aside for now, and everything, all the following will be about the electrics. גם. אבל יכול להיות שבחשמל כבר שמעתם על זה, אבל לא בסקלות המיקרוסקופיות, לא דיבר על פולריזציה, כל מיני דברים שבעיקרון עוד לא שמעתם עליהם. Okay, so this is the question we will be answering, okay? And so there are two types of influences. Two types of influences of the field E on a dielectric. Okay. Type 1 is called stretching, and I will explain in a second what I mean. And type 2 is rotating. Okay, I will now detail things. Okay, so let's start with a subtype of the dielectrics. Okay, I said I'm zooming on the dielectric, and within the dielectrics, I have three types of materials. Dielectrics. I have medium that are called polar medium, apolar, and electret. Okay, and now I'm going to explain about each of them. Okay, so A, polar medium. Now I will start with the apolar one. Okay, so let's give an example. Let's say I have I'm modeling an atom in a very, very simplistic way, where I remind you that all this discussion is starting because we said at the atomic level, there is no such thing as anything neutral. Okay, so let's zoom on an atom and model it. Okay, so when I have an atom, I have a nucleus with positive charges, okay? And I can model it, I can model the electrons as a cloud of uniformly negative charge, okay? Very simplistic model, okay? And because I don't want to remain in the naive answer, I'm asking, okay, what happens? I'm now imposing an electric field E0. I'm calling it E0 because I want to differentiate it from the electric field which will be generated in this situation. But I'm imposing an electric field E0. What's happening? Okay, so you tell me what's happening. What is moving? Where is moving?
The electrons will be mostly. The electrons will be mostly the other side.
So this will move up or down?
No.
The pluses.
Oh.
The pluses will be moving up, okay? Okay, so I'm not saying exactly if stuff are moving. There will be a relative movement of the plus against the minuses, right? You agree? And as a result of this, okay, this situation where the pluses and the minuses are moving relative to each other is generating what? A dipole. Okay, so I will have a dipole moment, which I can write as what? As Q and P, where N and P are the barycenters of the minuses and the pluses. Okay? The center of mass, if you want. Okay, centers of mass of the pluses and the minuses. Okay, now, of course, I'm assuming that the electric field here is strong enough to move the charges, but not as strong as to ionize the matter and separate completely the pluses and the minuses. Okay, it's just strong enough to generate this movement. Okay, and okay, so what E is doing? So this is the stretching effect. Okay, relative movement of the pluses and the minuses, and it breaks the spherical. So E breaks the spherical symmetry. Spherical symmetry. Okay, and if I turn E off, will I still have a dipole? Hmm? No, things will go back to the initial situation. Okay? So, in a sense, apolar medium is a little bit conducting. Okay? It's just conducting as much as the pluses and the minuses can move one relative to each other. Okay?
But does the atoms also move because we have polarization, like many dipoles?
Yes, so we'll talk later about what's happening when I have many dipoles, okay? But for now, what I wanted to show is what I mean by stretching, okay? I said there are two different effects of E on the matter. One effect is stretching. What is stretching? This, okay? Okay, so now this was the definition or the model, okay? And now I can define. I want to quantify it, okay? This was kind of a quantitative definition of this, but I want to quantify the answer of a apolar medium to an electric field. And the way I'm doing it is with the parameters called the atomic polarizability, which actually tells me how much the matter or the atom resists to the influence of the field E. Okay, so this is called atomic polarizability. Okay. And it quantifies the resistance or the answer of the material to stretching by an external field E. Okay? So we assume there could be all kinds of relations, okay? But we assume there is a relation of proportionality between what? Between E0 and P and the dipole moment. Okay, so P induced, okay, is alpha E0. Okay, this is the definition of the polarizability of alpha. Okay, and it tells me how conducting is my insulator. Okay, how conducting is the material. Okay, so
If the atom split, the material is conducting.
no, so it does. So it's still within the framework of insulators. So I'm assuming it's not splitting. It's only bound charges. I don't have free charges. I don't have ionization. Okay. So it's the insulator. We said the insulator is in fact every insulator is a little bit conducting. How much? By a factor that is quantified by the polarizability. Okay. Okay. And what does alpha depend on? You can guess. It depends on the structure of the atom. Okay. We'll give an example of this.
The size of the
Yeah, so everything that is related to the structure. This is a very simplistic model, but yes, the structure of it, the size, it's like geometrical parameters, and also physical conditions like the temperature. If you change the temperature, the polarizability of your material will change. And okay, and what are the, so you can check that the units of this are in the units of epsilon 0, m cube, check. Okay. Okay, so I'll give you just some examples, okay, so about the atoms that we're used to. Okay, so A, hydrogen, helium, lithium. Okay, just so that you have it, don't have to know it by heart. So this is alpha. Okay, so this is okay, so interestingly, the lithium is reacting. The lithium is an insulator that is very conducting in a sense. It's reacting very strongly to stretching. Okay. So now what I want to do is to What I want to do is to check if we could, with this very simplistic model, get these numbers. Okay? What? Yes.
How do we know it's proportional to the field?
We don't know. We just define it like this, and then it's empirical. Okay? You couldn't know it if I didn't tell you. Okay, I'm telling you, there is empirically there is a relation between the polarization, a linear relation between the dipole moment that appears that you can measure and the field.
There's no way to calculate and get it from the model?
Yes, so this is what we will do now.
So,
okay?
So it's not just
it's empirical because this model is not very real, right? But and also, like, people saw it empirically and then they measured the model fit, okay? But it was discovered empirically and it matches it works well with our models and with very simplistic models. Okay, so let's see if we can recover these numbers with the most simplistic model we can think of. Okay, so we will assume that we have a charge here plus Q. So let's model. Okay, so I have here charge plus Q, and here I have a sphere. It's not a shell, okay? It's a sphere that is charged in a volume. Okay, and the charge of this sphere is minus Q. Okay, so we apply E. We apply a field E. Okay, and then what happens? So E will be like this. Okay, so plus Q will move, plus Q and minus Q will move by a vector D. Okay, so this will be the new position of Q. Okay, and this is still minus Q. Okay, and we assume that the electron cloud is remaining spherical. Okay, we do all the simplest assumptions we could think of. Okay, and this is the displacement when at equilibrium. At some point there will be a situation of equilibrium, okay? The relative, the plus and the minuses will move relative to each other, but until a situation of equilibrium, and this is the displacement at equilibrium. Okay, and so Ex. Okay, this is the exterior. This is a field E that is imposed by the user. Okay, and in this situation, I will have a field E which is induced. Okay, because I have two charges, plus and minus. This will induce a field. Okay, induced E. Okay, and because I have equilibrium, I can write that this is what Itai referred to earlier, that Ex, they are cancelling each other. Okay, this is just Newton's law. Okay, if I have equilibrium, it means that the forces acting on each of these, the sum of the forces needs to be 0. Okay, so in the value, they are exactly equal. Okay, now we saw that the field at a distance E. We saw that the field at a distance D of a uniformly charged sphere is what? This is just very simple application of Gauss. Charged sphere is what, do you remember? Remember the
normal magnetic field from a point charge.
And it's QD divided by 4 pi epsilon 0 A3.
D.
Yes, D3. No, sorry, no, it's A, because, so A is A. It's not D, this is A. Okay, QD. And this is just, I can show it very quickly. This is just by applying Gauss. Okay, so you can do that E4 pi D square is Q enclosed divided by epsilon 0. Okay, and Q enclosed is the integral from 0 to D. Okay, because it's at a distance D of rho d tau. Okay, and rho is equal to 3q divided by 4p a cube, okay? Because it's uniformly charged, okay? Makes sense? Okay, so if you put this in here, you get that E4 pi d square is equal to 1 divided by epsilon 0, 3q enclosed divided by 4 pi a square d cube. Okay, so this cancel, this cancel. Okay, I've just applied simple Gauss. Okay, and this is this. Okay, pi also. Okay, so it's QD. I'm missing the cube. No, and this is cancelling with this, okay? So this is showing this, okay? Okay, so I know that the field at a distance d from a uniformly charged sphere is given by this. I know that this must be equal to the exterior field that I impose, otherwise I wouldn't have equilibrium. Okay, and so I know that this is equal to Ex. Okay, and it's also the induced field. But I remind you that what I want to do to model polarizability is to link between, I want to make the dipole moment appear, right? Because I want to link between the external field and the dipole moment. This is the whole point of the polarizability, okay? So P is equal to what in value? What is P, the dipole moment in this case? dq, right? Okay, so this is it, and it's here. Okay, so I can write that Ex is equal to P divided by 4 pi epsilon 0 a cubed. Okay, so this is the polarizability, right? You agree? By definition. Right? Because by this definition, this is alpha. And I can also write it as, you remember I told you that alpha is defined by the structure of the atom, okay? So in this case, the structure is entering this through A, okay? Just the size, the radius. Okay, I can also write it, so alpha, I can also express it as a function of the volume, right? The volume of my simple atom, okay? You agree? I have 4 pi 3, okay? Okay, now if you check it, okay, this is you know A for the hydrogen atom, and you know epsilon 0, so you can check if it matches. And it doesn't match, but it matches by a factor of 4, which is pretty amazing given how far this model is from reality. We didn't take into account any realistic quantum effects or anything, and still it matches by a factor of 4. So in order of magnitude terms, it's okay. It's a good enough model, okay? Okay, what's the time? Good. So this was for the atomic polarizability. And now I'd like to ask you what happens for molecules. So can I erase this? Okay, so I remind you we're still talking now about, so we are talking about insulators, and within the insulator we are talking about apolar medium, and we saw that apolar medium are reacting to a field by stretching, okay? So I looked at the case of an atom, a single atom, how is an atom stretched when I have an internal field? And now I want to ask, okay, what is happening when I have molecules? Okay, so, and you can already guess what will be a decisive difference between molecules. So, can you guess, like, what will it depend on, the reaction to stretching? Whether the molecule, the shape of the molecule, right? It will define whether it's stretching in this direction or this direction, okay? So it's not as simple. So for example, if I have CO2, CO and O, okay? You can guess that it will stretch more easily in some directions than in others, right? And because this is the case, I cannot, I won't be able to describe the polarizability by a single parameter anymore. What will I need if it depends on directions?
A matrix.
A matrix, a tensor. Okay, so in this case, I will define a tensor of polarizability. So P is going to be equal to A. Okay, okay, so I will have different reaction along different components. Okay, and this is also equal to AE. Okay, this is polarizability tensor. PBT tensor. Okay, okay, that will quantify the reaction, the resistance to stretching in various directions, components, along various components. Okay? Good. Okay, now, so we talked about apolar material. Now, what is a polar material? Can I erase this? So, a very good example of a polar material is, you know, water. Okay, so we said that in an apolar material, we don't have an intrinsic polarization, okay? If we apply a field, we have a polarization. I haven't defined it yet, but the polarization will be the density of dipole moments. Okay, my materials are made of many dipoles, and I can define density of dipole moments. Okay, but in an apolar medium, I don't have any intrinsic dipole moment. Okay, it appears from which effect? From stretching. Okay, and if I turn the field off, it disappears. Okay, in apolar material, I think it's B. No, sorry, polar materials. They are similar in the sense that they also don't have any intrinsic dipole moments. Okay, but it appears because of rotation. Slightly more complicated than this. So let's look at a glass of water, and let's look at the water molecule. Okay, so let's look at a water molecule. Okay, it's not a linear molecule like this one. We have H and H. Okay, here, if you remember, have an angle. Okay, and if you remember, these, the hydrogen, they tend to be more positive or more negative than the oxygen?
Positive.
Right, they tend, so this area tends to be more positive. Okay, and this more negative. So there is an intrinsic dipole. There is not, on average, there is no dipole. I will talk about it in a moment, but there exists an intrinsic dipole, okay? Okay, so this is different from the apolar. This is what makes the difference between them, okay? But on average, if I have a glass of water here, okay, the medium dipole moment is going to be 0. Okay? But then what happens if I impose an external field E0? What will happen?
The molecules will align.
Exactly, all the molecules will align. All the small dipoles will align. Okay, and then P is not going to be 0. Okay. And if I turn off the external field, it will go back to, okay? So intrinsically, I do have permanent dipole in a polar medium, but on average it cancels, and it's similar to the apolar situation in the sense that the moment you remove E, you also remove the overall the sum of all the dipoles, okay? Now let's just quantify P in the case of water, just because. Okay, so in the case of water, the dipole, the permanent dipole of water is 6.1 10 to the minus 30 coulomb meter. Okay, and let's see if we could have guessed this. Okay, now that you know the dipole, we wrote the dipole moment of an atom. Let's see if we can guess this. So P we know is QD, right? And Q is 1/6 10 to the minus 19 coulomb, right? And what's the typical size of an atom? D, 10 to the minus 10, right? 10 to the minus 10 meter. Okay, so in terms of order of magnitude, we're almost there. Okay, is it small? It's not small. It looks maybe small, but actually compared with other atoms, it's quite large. And this dipole moment, atomic dipole, molecular dipole moment, it explains many of the properties of water. For example, the fact that water is a good solvent. Okay, it's like that it dilutes things well. It's precisely because of the dipole. Because whenever you put an ion in water, all the dipoles will come and surround it, and this is what the ability of a material to surround another charge. This is exactly what quantifies how good the solvent is. Okay, so this property explains many of the properties of water, also the temperature at which it freezes and other things. Okay, so this is done. Okay, now let's say I just told you that it's rotating under the influence of a field, but let's convince ourselves that it's true. So why are dipoles rotating whenever I put a field E? So if I have, let's show rotation. Okay, so if I have two charges, minus Q and Q, okay, and a distance D here, okay, and I'm applying a field E. Okay, and what I want to show now is that this dipole will rotate and align with the field E. Okay, so if the field, if E is uniform, okay, I can write that F plus, okay, F on the charge plus will be equal to QE, right? And F on the charge minus will be minus QE, right? So the force cancels, but I have a torque, right? Which will be equal to N equal to R plus F plus. Okay, so this is R plus, This is R minus. Okay, plus R minus F minus. Okay, so this is going to be equal to D over 2 ER QE plus minus D over 2 ER minus QE. Okay, and this is going to be exactly, if you sum the two, this is going to be equal to QD ER E. Okay? So the torque is, the sum of the forces is zero, but the torque is non-zero, and this will tend to rotate the two until what? Until the torque is zero, and then there is no more rotation. Okay? And so the torque N, I can also write it as a function of the dipole moment, right? Because QD is the dipole moment. Okay, and it's oriented in a way that will tend to align P and E, right? Because P cross E will be equal to 0 on the line. Okay, so I talked about two types of insulators. There is a third type which we are less familiar with, okay, which are called electret. And or sometimes they are called pro-electrics materials. Okay, and these are materials for which when you turn the field off, the dipole will remain. Okay, in both the situations that I described, if I turned E off, the total dipole would go back to 0. So in the case of electret, this is no longer the case. You can reach this with all kinds. You can freeze water with a magnet, and then it will remain polarized in the directions in which you freeze it, etc. But these are cases where the dipole is remaining even after you turn the E off. Okay, so if I summarize, okay, I have three types of medians which I can classify according to the effect of an external of E. Okay, so I have apolar, polar, and electret. Here the effect is to do stretching. Here rotating. So here I have an induced P. And here, P is permanent. Okay, so this summarizes all the properties that we talked about. Okay, so one was talking about different types of materials and specifically insulators. Then the second point will be to discuss more generally what's the general questions that we are asking in electrostatics in matter. So two general question of electromagnetism in a material. Okay, and the question is the following. I have an external field E0, okay, which is generating what? In a material, we saw now that if I put a material in a field E0, what's happening?
Dipoles are created.
Okay, dipoles are created. It's generating a dipole moment of polarization. Okay, so P, this is big P. It's a bit confusing, but in every book there is a small p is the dipole moment, the local dipole moment, and big P is the polarizability, the polarization, which is the volume density of dipole moments. Okay, so this is polarization. We'll define it formally later. Okay, so density of dipole moments. Okay? Okay, now this polarization is inducing what?
Field.
It's inducing a field, right? The moment I have, this relates to what we did with the multiple expansion, okay? The presence of a difference in charges, minus and pluses, is generating a potential, is generating a field. Okay, so this is E, this is generating E induced. But then E induced is adding up to E0, right? So the new E in which my matter is, my material is standing is the sum of the original field E0 and the field that was induced by the very presence of E0. Okay? And so you see that there is an issue here of something is circular, there will be a problem of keeping things consistent, right? How do I calculate this when this influences this and this influences this, etc. Okay? Now, if I give numbers to each of these things, so what we did until now was to talk about one, okay? When I described to do the different kinds of materials, I said, okay, for several types of materials, I'm applying E0. How will it affect the polarizability, the dipole moment of the material? This is what we did in the last half hour. Now, what I will want to focus on is 2, okay? What is the field that is generated by a material that has been polarized, okay? Okay, so this brings me to 3, which will keep us busy for the rest of the lecture today. The field induced by a dielectric material. Okay, but the reason I summarize this, you should have in mind that when I'm talking about a material in a field, there are 2 issues, and there is a matter of circularity, that the material is reacting by generating dipoles, and the dipoles in turn are generating a field, and this all is circularly problematic. Okay?
Ma'am, do you mean 2?
No, 3? You mean, okay, I can call it, it's just these are the points,
Okay.
and these are, okay? It's confusing, you can number it with letters, okay? But this is the 3rd point in the chapter, okay? So it's 2 in the diagram, okay? Now we will derive it formally, okay? We will write it rigorously. But before we leave for the break, I would like to release you to the break with the intuition of with an intuitive answer to this question, okay? Okay. So let's start with intuitions. Okay, so this is A under 3, intuitions. Intuition. Okay, so you already see that we will have an issue too. What we want to answer is 2. Okay, I have a polarization. I want to calculate the induced field. Now, you already see. So you already see that we have an issue here because how did we calculate fields so far? What did we need to calculate fields? What was our charges, right? Our only chance to be able to calculate the field formally is if we have charges. Okay, so somehow, in order to relate this and this, we need to relate the polarization with some measure of the charges. Okay?
This should be the placement of the charges, and then it changes the place of the charges, and then the field acting.
Exactly. Exactly. So our chance to calculate our chance of calculating E induced is if we can relate P, the polarization, to some measure of, if we can relate or translate, okay? Translate P into some measure of a charge distribution, okay? If we cannot do this, we have no chance to calculate the field. Okay? So the question becomes, can we translate P into a charge distribution? And I will give you 2 cases where we will try to get an intuition. Okay, so the first case is the following case. I'm drawing here dipoles. Okay, so I'm drawing them with these are plus, these are minuses. Okay. Okay, and what I've made here is a uniform polarization. Do you agree? Inon, do you agree? Yes, you agree that this polarization is uniform, right? Polarization, we said, is density, volume density of dipoles, and I've drew them uniformly. So the polarization here is uniform, okay? And you see that inside the material, locally, the pluses and the minus will cancel, right? So locally, inside the material in which I have a uniform polarization, do I have a charge? No. Where do I have some charges? On the borders, right? At the surface. So the pluses and the minuses will cancel everywhere except at the surface. Okay? And so this will lead to a surface density. I will derive it formally after the break, but this is the intuition. So this a uniform polarization will result in a surface density of charges at the 2 extremities, right? Now, what happens if I have a polarization which is not quite uniform? Okay, so I'm removing it from here, I'm putting it here, and here I'm adding. Okay, this is a non-uniform polarization, right? Right, but if doing a superposition, you're already going into the calculation. But intuitively, what it means is that I will have areas in the volume where I will have some charge, okay? Because the pluses and the minuses will not cancel anymore, okay? So if I have a non-uniform polarization, okay, density of dipoles, okay, this will result in a volume density, or it should be translatable mathematically into a volume density of charges. Okay? So what we will do after the break is to try to derive these densities rigorously and then translate these densities into E. Okay? My goal in the next 40 minutes is to give you the methods to go from this to this, okay? To do the two transitions, okay? And this will be the key to many exercises. So my goal now is to give you the method, and I will first show you formally that the polarization can be translated into charges, okay, surface charges and volume density of charges, okay, and then the moment we do this, we can use all our arsenal of tools, which we already remember. I did this triangle between rho, E, and V, okay. We will write a Gauss theorem inside the materials, etc. But the first step is to translate polarization into charges. Okay? So this is this first step. Okay, okay, we showed the intuition. This is what we want to show. That a uniform P translates into a surface density and a non-uniform P into a volume density. So let's draw again our drawing that we had for the one we did for the dipole. So here I have a small box of the electric material. Okay. Here I have O, and it's always the same. ON is R prime. Okay, this is M. Okay, so OM is equal to R. This is D tau N. R minus R prime, okay, and this I will also call it R star, okay? Okay, so the rigorous derivation. Okay, so what did we show? I will tell you what I'm going to do, okay? And then it will be easier to follow. So I want to translate polarizability into charges, okay? And I know to link potentials and charges, right? How do I link potential and charges with these big integrals, right? Right? I have the integrals that link the potential and the charges and the distribution of charges, okay? So what I will try to do now, I will try to write the potential as a big integral, okay, on volume. I will try to write it as one integral on the volume and one integral on the surface, okay? Where here I will have something that is related to the polarization and here too. okay, and other things. But I also know that this, I also know how to write this as a function of rho and sigma, right? Right? So after I do this and this, I will be able to identify the terms. Okay, do you understand? I don't want to just do it and then you'll be surprised by it. So I want to explain you what I'm going to do. Okay, I'm going to try to write the potential as two integrals, okay, where I will make P appear somehow. And then I will be able to say, okay, but I also know that V is a volume integral on rho and on sigma. So this must be equal to this and this must be equal to this. Okay, this is what I'm going to do. Make sense? Okay, so let's do it. So we showed last time that for one dipole, Vm is equal to what? This is from last time. How do I write the potential from one dipole as a function of the dipole moment?
Q over 4 pi
If I have the dipole P and M, you remember this? Rings a bell? Okay, this I showed last time. This is the reason I showed it last time. Okay, this is for one dipole. Okay, now what is the polarization? The polarization is the volume density of many dipoles. Okay, so I can write that P by definition is equal to the limit when d tau goes to 0 to the sum of many dipole dipole moments of one dipoles divided by delta tau, okay? And I can also write dp infinitesimally, okay? So the dipole moments, you should be careful here where is a small p and where it's a large p. Okay, and I'm going to try to exaggerate it a bit. Okay, so this is the definition of the polarization. Okay, it's the volume derivative of the dipole moment, volume density of the dipole moment. Okay, and so if I replace here, I can write that did V. Okay, I'm moving to infinitesimal writing here. Okay, so did V is equal to did P 4 pi epsilon 0. And what do I have here? What is Nm? Is R star, right? R star, and here I have R star cube. Okay, and this is also equal if I replace here to P, the polarization at point N, okay, d tau 4 pi epsilon 0 R star cube, and what am I missing here? R star. Okay, so this is did V. And what I want is the total V. So I want to make an integral appear, right? Right? So I can write that Vm is equal to the integral over the volume, okay, of Pn, it's large P, Nm, 4 pi epsilon 0, Nm d tau.
What about the part of the monodipole?
What?
What about the part of the monodipole? Because you have dipoles and also the
but here I'm looking at only yes. I'm looking at I don't have monopoles. I only have dipoles. It's also correspond to the reality of a neutral material where all my atoms or molecules are small dipoles, and I'm asking, okay, so I know how to write the potential from one dipole, and now I'm integrating it over the entire volume. What will be the total potential?
But you can have
There is
monopoles, no?
What?
But you can have
But not in my neutral. I don't have monopoles in my neutral dielectric. Okay, so this is V. Now I told you that in order to identify this with charges, okay, I want to make appear something that I know that I can identify. Okay, so I will use two things now. We use two identities. Okay, the first one is to write that the gradient, I'm putting here a dot because it's as a function of n, okay? I'm deriving on the, it will become clearer in a second, of 1 over nm is equal to minus nm. Okay, another way to write it is the gradient of 1 over r star is equal to minus r star over r star cube. Okay, this is not trivial, and I will let you show it at home. It's also in the preface. Okay, and the way to show it is to simply write things. Okay, if you write it in Cartesian coordinates, for example, I'll give you the very beginning, and you just need to make sure it all fits. But 1 over nm, okay, it's equal to 1 over a big square root, right, of xm minus xn, okay, square plus ym minus yn square plus zm minus zn square, okay, and the gradient here is according to n, okay, so it's basically yn dzn. Okay, so if you do it, it will work. Just make sure it works, okay? So this is the first thing I want to use. And the second identity I want to use is the following. I will want to use that the divergence of FA is equal to F divergence of A plus A grad of F. Okay? So I'm going to use both these identities. Okay, and I will open this. Okay, I will open this with these two ingredients. Okay, so let's open this. So okay, I'm first using number 1, okay, and I can write. So I'm going to take this, okay? This, I'm going to use that in the grad of 1 over nm, okay? So by using 1, I can write that this is minus the integral on the volume of P of n grad of 1 over nm. Okay? Just using this. Over 4 pi epsilon 0 d tau. You agree? Everybody agrees?
Yes.
Just replacing things. Now I want to use the second one, and so this will play the role of A here. Okay, and this will play the role of F. Okay, so if I use the second identity, okay, I can replace things by 1 over 4 pi epsilon 0, the integral on the volume. So I have A grad F, okay, so that's going to be the integral of the divergence of FA, so Pn over Nm, right? Minus, okay, this term goes here, minus 1 over Nm, divergence of P. Everybody agrees? Do I agree with myself? Yes. Yes, I agree with myself. Okay. So, and now I remind you, what do I want to do? My agenda is to make some surface integral appear too, right? So, what do I need to do to change משפט הדיווגנס? Green's theorem, so I can write that this is equal to 4 pi epsilon 0, a surface integral of Pn dsx, okay, that's a surface pointing outward, over Nm, 1 second, plus 1 over 4 pi epsilon 0 minus divergence of P divided by Nm. d tau. Okay? Yes. I'm not sure שחסר מינוס, כי אולי כאן A grad F is equal to div minus F divergence of A. כן, נראה שחסר מינוס. Okay, זה lost minus here. טוב.
כי יש שם, אחרי השוויונים אחד יש מינוס והורדת אותו.
פה, נכון. אז אני לא יודעת לאן הוא נעלם.
הזהות פשוט כאילו קצת מינוס, בגלל 2.
בזהות 1 יש פלוס?
לא, פשוט הורדת את המינוס. כאילו,
צריך לשים מינוס לפני הכל.
נכון, אבל זה התשובה, אז לכן יש לנו בעיה. Okay, so I'm writing here lost minus, and because it will not prevent me from making my point, okay? Worst case scenario, it will be a point up to a minus, but I want to make the point, okay? And we'll solve this minus things by next time, but I want to make the point, okay? So I'm writing it here, and I promise that next time I will tell you where it disappeared. it's possible that the identity is without a minus, but I will check this. I just don't want to waste time on this because I need to reach some methods for you for the exercises. Okay. Okay. So once that we have this, okay, let's assume that we are fine with the minus, and I remind you that we know that Vm is by definition of a surface of a volume density. Okay, this we know. Okay, and it's also by definition of a surface density ds and m. Okay, and so this is where I want to identify. This is the identification I told you I want to do. So what will be the sigma and rho? Sigma and rho. I'm listening to you guys. So sigma is p nx, right? Because I want the nx ds to be equal to
What is the
ds.
NX?
So nx is a vector, unit vector pointing outside of the surface. You agree? Unit this by ds is dsx, okay? And rho is equal to what?
Minus d.
So sigma pole, rho is going to be minus the divergence of p. This you need to know by heart. Okay? And so we won, okay? So V in this context, Vm is equal to 1 over 4 pi epsilon 0, sigma pole Nm Nm ds plus okay? Okay, and the good news is that if we apply the you see that rho pole d tau is equal, it's equal by definition by to minus the divergence of p d tau, right? And this, through Green's theorem, is also equal to what?
The surface.
To the surface of p ds, right?
Yes.
Okay, and this is also equal to, by the definition of sigma pole polarization, of sigma pole ds, right? So the sum of them is 0, right? Which is a good news because overall, it's true that that the polarization led to some surface charges and volume charges, but overall the dielectric is neutral. Okay, so we're okay. Good news. Okay, the total charge is 0. Pole d tau plus sigma pole ds is equal to 0. Okay? Good. So now I'm going to make two smaller remarks which are very important. Okay, so the first remark is that sometimes in books, and this is also the way I studied it at the time, they make you think that it's some kind, it's another trick that we're using, that in the presence of polarization, there are some kind of fictitious charges. Okay, everything is similar to a situation where we have surface charges and volume charges, but like just fictive charges which I'm imagining to be in an equivalent situation, etc. And this is not the case, okay? There is nothing fictive here, it's not a trick, it's really happening whenever I have polarization, and this is what I showed you with the small intuitive drawing. If I have polarization, I have real densities of, real surface densities of charges and real volume densities of charges, okay? So first point is that it's not another mathematical trick or something we imagine. We have real charges on the surface and in the volume the moment we have a polarization. Okay, and the other remark I wanted to make is a methodological remark. Okay, so remark 1, not a trick. And if you don't know what I'm talking about, it's fine, but just in several books they will present it as a trick and it's not, okay? Second remark is a methodological one for exercises, methodological remark. Okay, and the point here is that if you have a polarization in an exercise, okay, you need to calculate sigma and rho with this formula. And then we're back in the situations we know where we can calculate the field, the potential from surface densities. Okay, so this is the way to solve an exercise where you have polarization. Okay, you need to bring it, to translate it into charges and then go on. And it doesn't mean it's not going to be hard, okay? It might be a very hard exercise, but you need to put yourself in the known situation, okay?
When you have a uniform density, the rho is going to be 0, and then the sigma is going to be the charges on the borders. So, like, sigma is always telling us what the charges in the borders, and the rho is going to tell us the charges in the volume?
Yes.
Okay.
Yes, exactly. Like these two things are just the mathematical translations of what we showed with the intuition earlier. Okay? Okay, now what happens if we also have okay, I'm going to, in the time we have, I'm going to give you two more, I can't remember which points we are, I think it's 4. Okay, so the idea here is that we managed to bring ourselves in the known situation where we are linking between charges and potentials and fields, okay? And the moment we did this, we can use our usual arsenal of tools. And one of the important tools was the Gauss theorem, right? So can I write a Gauss theorem inside the material? The answer is yes, okay? And this will also be very important for exercises. Okay, so let's derive it. So rho tot is going to be equal to the sum of the bound charges plus the free charges, right? Now, usually in exercises we have 0 handle on the bound charges. Okay, the way we can handle bound charges is through the polarization. And I can write the Gauss theorem for rho tot. Okay, so I have div of E equal to, you remind me, the Maxwell equation. Rho tot divided by epsilon 0. Okay, so I can divide it into rho free. Okay, these are free charges and bound charges plus rho bound divided by epsilon 0. Okay, and this I can replace. So this, of course, is true for the bound charges. I didn't write it, but everything we've done was for bound charges, right? I don't have any free charges in a dielectric. So I can replace this with minus div of P divided by epsilon 0 plus rho free divided by epsilon 0. okay? Which means that divergence of epsilon 0 E plus P is equal to rho free. Okay? Now, I will define a vector which is called the displacement vector. In Hebrew it's העתק. Okay? Displacement. Okay? And the Gauss theorem inside the material, it writes like this, rho free. And what I gained here, okay, I only use the definition, but what I gained here is that I can say nothing on rho bounds, as I said in exercises. It's much more easy to deal with rho free. Okay, so I'll tell you about the so this is the integral form is going to be this. Q free and closed. Okay, this is the Gauss theorem inside the material. Okay, so E and D are playing the same role. Okay, and this is a very good methodological news. Why? Because the way to solve exercises is going to be the following. You know rho free. And so from rho free you get D. Okay? And from D you get E if P is known. The rho bounds are hiding here in P. Okay? This is the key of the method of many exercises in the electrics. Okay? You're given P, you're given rho free. So you can calculate from the Gauss theorem, you can calculate D, and because you know P, you can deduce E. Okay? This is super important. And I'm going to make two very quick comments. And then I will just give you one more definition, which you will need for exercises. Okay, so one important comment. So D is the analog of E in the electrics, right? Because you can write a Gauss theorem in the same way we could write a Gauss theorem for E in vacuum. But you should be very careful about the analogy. Okay, so first, the divergence of a vector doesn't entirely define the vector. Okay, so there is many things that you can say about E which you cannot say about E just because they are analogous. For example, rho of D is not 0. Okay, it would be tempting to say, okay, so I know that rho of E is 0 and E is the analogous of D, so maybe rho of D is 0 and then do all kind of things. You can't, okay? The only thing you can do is write the Gauss theorem for D. And don't push the analogy because it could play tricks to you in exercises. Okay, so comments. Okay, so one. So rho of D in general is not 0. Okay, so be careful with the D E analogy. Okay, it's limited to the Gauss theorem. Okay, and the last thing that I will do is to define for you what's a linear. So we will have several exercises to practice this. Okay, this is very important. And I will just give you the definition of a linear medium because you will also need it for the exercises. So okay, Gauss theorem. And 5 is linear medium. Okay, so a linear medium is one type of the electric medium. Okay, it's a subtype of the electrics. Okay, and it's a medium for which, so the definition, it's a medium for which the polarization is proportional. This you might have seen in previous lecture, in previous courses, okay? The polarization and the field E are proportional, and this is what we call the susceptibility. Susceptibility. Sometimes, okay? And why is it interesting to write it this way? Because if I write the displacement for such a medium, so D by definition is epsilon 0 E plus P. So if I replace, it's epsilon 0 E plus Q E P. Right? No. Epsilon 0 plus epsilon 0. I can take, it's epsilon 0 E 1 plus K. Okay, and this is the electric coefficient. Okay, which you also might have heard of. Actually, the dielectric coefficient is it's not exactly this. It's this, okay? This is equal to epsilon 0, 1 plus K. Okay, so the important thing to remember is that with this definition, for a linear medium, the polarization is proportional to the field, okay? And the consequence of this is that the displacement is also proportional to the field. And thanks to all kind of things I defined, okay, this is the link between the electric coefficient, the susceptibility, etc. These are notions that you might need in exercise. Okay, so we'll meet. Good question when we will meet. Yes.
Next week,
So just asking why we happen to have linear mediums.
For now, it's a definition that I'm giving you. It's just some mediums are behaving like this. Obviously, they are very useful in exercise because they allow you to do all kinds of simplifications. But for the moment, I'm only giving this as a definition. We will develop on this when we talk about waves. Okay. Right. So next week there is no lecture. And I'm trying to see how to not make you lose too many lectures because this semester is already pretty short. But on the other hand, when I did Shiur Hashlama, there were like 3 people. So does it help you? Do you see the recordings? What?
It's recorded, so.
Can I ask why you don't come on Monday?
It's 8 a.m.
Ma?
It was at 8 a.m.
The 8th thing is
I have another lecture.
But isn't it supposed to be that the שעות מחלקה עוברים? זה לא by definition, זמן שכולם...
כולם יכולים, אבל כולם לא רוצים לבוא כל כך מוקדם.
לא, זהו, אז זאת השאלה שלי. זה עניין של מוקדם או שלחלקכם יש קורסים?
לא נכון להגיד ככה.
מה זה?
כאילו דו-חוגי, אז בדרך כלל...
הבנתי. חשבתי שהשעות מחלקה הם כאילו by definition זמן שמתאים לכולם.
בתוך המחלקה יש עוד...
הבנתי. טוב, okay, so we may do not this coming Monday, but the Monday after I may do a lecture with whoever comes. The other option is that I will tell you watch the lecture from last year on YouTube, but it's in Hebrew, so we cannot do this. So, okay, so we'll think about it. I will send you an email, and in the meantime, חג שמח.
לך יש שעות מחר, שיש לי קורס בפיזיקה. זה גם יכול להיות.
מאוד הגיוני כי אפילו שנים.
הוא לא מופיע אני בחופש. שמע, אני צריך להוריש להם לבדוק מה שיש לי במעבדה אחת נספיק בשביל לעבוד.
מה?
הם ענו לי בסלייק, אמר לי ששלח לי במייל, בסילבוס אין גם הבנתי את הדבר. אין מייל של החוס. אז אני עכשיו שאלתי אותו בסלייק 3 דקות אחרי עם המייל.
Organization זה צפיפות מומנטים.
לא, אבל...
יש לך מלא טיפולים.
דיברתי איתו.